ourselves off last class was still discussing this postage stamp problem, and we just have a little bit to wrap up there. So we were considering this, I remember this postage stamp problem. Which basically was something like this. So given positive integers a and b, the question is for what integers c is it possible to find non-negative integers. So this is a key word here. Non-negative integers x and y such that ax plus by equals c. So this is the problem we're looking at. Most of our discussion will be about the case where a and b are relatively prime to each other. And if a and b are relatively prime, and if you throw out this non-negativity requirement, then the answer to this question would be all c are fine. Right? Like all c would have solutions. It's just given a c such you can find integers x and y such that this is true doesn't mean you can find non-negative ones. So that's an extra twist. And then what we found out was this one, or this fact. Just remind you of something we proved. Was that if a and b are both positive, and in fact we're assuming bigger than 2 here. The problem is pretty trivial if 1 is 1, by the way. But anyway, if a and b are both positive, bigger than 1, and relatively prime, there are no non-negative integers x and y with the property that ax plus by comes out to be this number, a times b minus a minus b. So in the language we were using, this was an infeasible thing. You could not make this quantity using non-negative multiples of a and b, adding them together. Okay, so this quantity is significant. It's not feasible, but it's significant because it's the last non-feasible thing. So everything after is going to turn out to be feasible, and that's the remainder of our discussion. We're going to prove that fact, that anything larger than that will be feasible. So here's our proposition 3, 4. So assume a and b are positive integers, which are relatively prime. So the statement is that if you take something which is larger than this, okay, so we'll write it as something that's at least the next number after that one. So if n is at least ab minus a minus b plus 1, that's at least as big as the next number, then the statement is it will be feasible. So the statement is then there are non-negative integers x and y which satisfy ax plus by is this number n. Okay, so anything beyond this point is going to be feasible in this postage stamp type problem. Okay, so I know we have to prove this, and like the last proof we did when we were doing this other thing over here we did this one last class, we're still going to rely on the theorem we proved about solution sets of Diophantine equations. Right? And the theorem about solution set of Diophantine equations tells us all of the possible solutions to equations like this, including with like positive and negative choices for the x and y. Okay, but we're still going to use that theory, and if we assume, since we're assuming relatively prime here, this Diophantine equation will always have solutions no matter what. Okay, because the GCD is a divisor of n. GCD is 1. So anyway, what we know this thing has solutions. So as far as this proof goes, we're going to start out by just invoking one. So let's suppose we have one, which we do know exists, right? So let's let x naught y naught be just some solution. So this is going to be an integer solution to the equation ax plus by equals n. We know this exists because, as I said, the GCD of a and b divides n. Okay, such a thing exists. And then from that one solution, you could give a description of all solutions. Okay, so let's remind ourselves that theorem. So all other solutions have the specific form that the x value should be the 1x you know plus a multiple of b, and the y value should be the one you know minus like the same multiple of a for an integer t. Okay, so this one solution we just conjured up out of the air that we just know it exists. We don't know anything about the x and y in terms of if they're positive or negative. Okay, so the issue for us is to cook it up so that these things are both positive, or rather non-negative. So we have freedom over t, basically. You want to choose t in such a way, if possible, right? Our hope is to choose t in such a way that this is non-negative and that is also non-negative. Okay, and so here is just the rough idea where this is coming from for what we're about to do. So let's just pretend y is humongous, or y naught, you know. Pretend the y naught we were given was some oversized, humongous positive integer. Okay. Now, if y is massive, massively large, unnecessarily large, what's going to happen is you have to take away a lot of a's to cut it down to n. Okay. So the larger y is, the more likely x is negative, right? So pretend, let's just say y is really big. What would you want to do is you'd want to actually cut it down in size to try to balance out x, to bring x up. Balance the scales, so to speak. So if y was really big, what you really want to do is take away a lot of multiples of a from it to make it as small as you can while keeping it non-negative. Okay, and in fact, this is like a remainder in division, right? Like if you divided y naught by a in division, what are you doing? You're seeing how many multiples can you take away until you get something that's almost negative, but not quite. So we're actually going to invoke the division algorithm here to get this right. So we have to figure out what t is supposed to be, and what we'll do is this. We'll think about what happens when you divide y naught by a as in division. So let's divide y naught by a. You know, this is like as in the division algorithm to get a quotient and a remainder. So this will give you a quotient and a remainder, which satisfy that y naught is a times the quotient plus the remainder. Okay, and the key fact about remainders is they are non-negative and they do not exceed the divisor. Okay, so what we're going to do is we're going to, going back to our parametric description of solutions, we're going to take the solution that has the property that t is q. Okay, so for this quotient that pops out of the division process, we're going to consider the solution. We'll call it x1, y1 to this thing up here. That corresponds to when t is q. Right, so that means x1 is x naught plus bq, and y1 is y naught minus aq. Okay. Now, the thing about doing this so far is the y naught that, or sorry, the y1 that comes out of this process is what you get when you take away all these multiples of a. Right, but what's y naught minus aq? Where's our division equation here? Right, so y naught minus aq is actually r, exactly, the remainder r. So notice that y1 is y naught minus aq equals r. That's how we cook this thing up. So what we have, notably, first of all, is that's non-negative. So our y is non-negative. So that's half of what we want. The other thing that'll be relevant is it's not too big either. So we'll take advantage of that in a little bit. But y1 and r are the same thing, so that's true because it's true for r. Okay, so all we really have to do is show that the x1 we built over there is also non-negative. Okay, so we need to show that x1 is non-negative. Okay, and so let me just, let's just lay out some facts we have. Okay? So let me just remind us a couple things. So note that we have the following things. So the one thing that n has to get brought back into the story at some point. But n is assumed to be at least ab minus a minus b plus 1. Remember that assumption. And this thing above, I want to work with this for a second because it'll play a role in a moment. But y1's an integer less than a, so since it's an integer, it's certainly true that I could write this instead. If I write less than or equal, right? Because it's an integer less than a, then it cannot exceed a minus 1, the next lowest integer underneath a. So we'll write that fact. And then in a minute, we'll use the following fact, which if I multiply this by minus 1, this is true. So we'll use that in a second. Okay, and additionally, let me also say, just to start the next part, right? So the other thing we know about the relationship between x1 and y1 is they solve this Diophantine equation, wherever it is, this one, right? So x1 and y1 solve this equation. So it is true that ax1 plus by1 does equal n. Okay, and that's where we're going to start with x to try to understand x1. So what we can do to this equation is solve it for x1 and then try to say something about what's on the other side. Okay, so if you solve this for x1, what you would get is that x1 is n minus by1 divided by a. Right? So, okay, and now what? So now is where you use some of the inequalities on that I wrote above just to set the stage here. So n is at least this. So we're going to make an inequality. Okay, so this is greater than or equal what you would get if you replaced n with this thing that is greater than or equal to. So let's put that here. Okay, but also, since y1 is less than or equal to a minus 1, this minus a multiple of y1 is going to be greater than or equal to minus this. So we're just using this inequality as well. Okay, so using this and also this sort of together right here. To get some kind of expression that's really all about just a's and b's. Okay? Now, what is this actually? Let me write it above. Okay, so what's going on over here? Do some algebra. I guess this says, all right, so this, there's an AB that pops out of this minus AB that'll cancel this AB. And also over here, there is a plus b, cancels this minus b, right? So this will cancel what happens there, and then this one will cancel what happens there. And then there's only two terms left above, so there is negative a plus 1. Okay? What's that? Look. Let's split this up. You have minus a over a is minus 1, and then 1 over a is 1 over a. Okay, you have this. So that's the same expression as above. So x1 is at least minus 1 plus a little, basically. Right? So a is positive. Okay, so a is positive, so this looks like you're adding a little fraction to minus 1 to make it a little more positive. But x1 is an integer, and this is telling you, right, so this is greater than minus 1. That being strictly greater than minus 1. But x1 is an integer, so it has to be at least 0. Okay, so have an integer on hand that we know is strictly larger than minus 1, so that means it has to be at least 0. And that's exactly what we needed. That's exactly what we wanted to prove. We built this x1, y1, which we know solves the Diophantine equation. We cooked it up so that y1 was non-negative, and then we justified that the x1 we had was also non-negative. So there it is. So that's our solution to this, this problem. Okay? So it always exists under these circumstances where which was erased, but where this is true. Okay, so that finishes the proof that AB minus A minus B is actually the last non-feasible value. Okay? You guys have any questions on this proof? Okay. Yes?
Can you explain the motivation again to divide the y naught by a?
Well, because you're, well, you want it, the idea, again, is because whenever x goes up, or whenever y goes up, x goes down, right? And so you got this sort of scale state, but there's the line here, which is where 0 is, and you want them kind of both above that, so to speak. So the idea is to lower y as much as possible without crossing that line, because that should raise x as much as possible, and then you just hope it got across the finish line there, which it did. So, okay, so the idea is lower it as much as you can. How are you free to lower it? This is saying you could subtract as many multiples of a as you want. Okay, and that's essentially what division is, right? You just see how many multiples of a can I take away from this number before I get into the negative region, right? And so that's what it's about. So then it was just sort of formally done by invoking the division algorithm. But I mean, you could have probably argued it the same way if you wanted, like just to say, like, let's let t be the greatest integer such that this is non-negative. It's the same thing. Does that make sense? Okay. Okay, so that's the motivation. So it's So anyway, one last thing about this problem. I mean, we did some silly examples in class involving like really small numbers, like stamps that cost 3 and 5 cents, or some football game thing with scores of 3 and 7. But now we understand what's happening in general, and I got to tell you, stamps have gotten a lot more expensive. But if you want to know where we're at right now, between the year 2026, I looked this up recently. So regular stamps cost 78 cents now. And then I wanted another kind of stamp. So you could also buy postcard stamps. Postcard stamps. Cost 61 cents. Okay, so let's just run with these numbers. So let's just say we wanted to do the postage stamp problem with these two types of stamps and say, well, if we're can use any kind of combination of these stamps as we want on our mail. What's the question you guys? What are the feasible postage amounts? What is the largest non-feasible postage amount? And now we know how to answer that. Okay, so the largest. Well, actually, before I say anything about this, I would like to point out something to you about these numbers. So for the results that we've been stating, they're supposed to be relatively prime. In this case, they are. 61 is a prime number, in fact, and it doesn't divide 78. So They are in fact relatively prime to each other, so let's point that out. So GCD of 78 and 61 is in fact 1. So we can apply our theorems, and the largest non-feasible postage amount. Now we know it would be A times B minus A minus B. So that's 78 times 61 minus 78 minus 61 would be in cents. And so you figure out what that is. That's a big number. Just, I just figured it out in advance, but it's 4,619 cents. So that would be $46.19. Okay, but the theorem we proved says that if we are ever anything beyond that point, 4620 or 4621 or whatever, anything beyond that you can make by some combination of these things. Okay, that's what we proved. Okay. Any questions? Yes.
Was the theorem only for relatively prime?
The theorems were only for relatively prime things. So what you want to think about if it's not relatively prime is, well, first of all, your results from Diophantine equations that say you only ever have solutions when the right-hand side's a multiple of the GCD. So it's worth talking about when the right-hand side's a multiple of the GCD. But what you can always do with this kind of stuff, if you're looking at one of these equations and the right-hand side's a multiple of the GCD of A and B, you could divide the equation out by the GCD, and then you put yourself in the case where they are relatively prime. Then you can apply the theorems. Then you could like reinterpret it in terms of your original equation. So that's what you want to think about.
And is A always the larger number?
No, I don't think we made any assumption about which was bigger. And the discussion was symmetric, so it doesn't really matter. Yeah, the formula. Notice the formula is symmetric too, but it doesn't matter.
Yeah.
Okay. Anything else right now? Okay. So we're going to shift gears to something different. I guess I did tell you we have a quiz on Friday. The sort of cutoff of things that I'm going to potentially ask you about is right here. Okay. So just up to this. This is sort of the end of our discussion on linear Diophantine equations, and now we'll start talking about something else. Okay. That's also coincides with what's on your homework that's due Wednesday. Everybody have a homework due Wednesday. Okay, so we're going to talk a bit about induction now. I mean, it's quite possible you're comfortable with induction or perhaps not, but either way, we'll spend a little time just going over it because it's a useful tool when you're working with integers. Okay, we'll also talk a little bit about something called the well-ordering principle, which we have used a few times without making a big deal out of it. So we'll talk about the well-ordering principle and mathematical induction, with an eye towards how we're going to use it in this course. So this material in the textbook is in an appendix. So appendix A.3 if you want to look to a source. So anyway, let's start with the well-ordering principle. This is a very intuitive statement. So the well-ordering principle says the following facts, that every non-empty subset of positive integers has a smallest element. All right, so if you have any collection at all, even if it's an infinite collection of positive integers, it will always have a smallest element, right? And that's because, well, I mean, it's supposed to make sense, I think. But it doesn't matter if you have a ton of them out to infinity. We're talking about what's small, and then the small ones can't go past 0, right? So it kind of makes sense. Eventually, you kind of stop somewhere. But I mean, the thing about integers is they always have, you know, a certain amount of space between them. The thing that should be said about this fact, though, is that if you tried to like change the word integer to be real number, then this is a false statement. Okay, like if you have, like, you could have non-empty subsets of positive real numbers that don't have a smallest element, and I mean the kind of thing you could have for that is like the interval from 3 to 5 or something. Like that's as an interval of real numbers. It's non-empty. They're all positive. There is no smallest element in the set because 3 is not in the set, right? So there's lots of things that are really close to 3, but there's nothing in there that's smaller than everything else that's in there. Okay, so that's the kind of thing that should just be brought up to contrast this. But this is about integers and a very believable thing. But we use it a few times, in fact, even when we, I think, proved the division algorithm. I think we used it when we proved every integer has a prime divisor. Every positive integer has a problem. Positive integer greater than or equal to 2 has a prime divisor. We actually use this as well. And so I will show you another case where we will use this. So let's use this. To prove something that we technically didn't prove that we probably should have, so we're going to give what's called a non-constructive proof of the following theorem. So this is a theorem we've been constantly using, theorem 212. So the theorem that when you have two integers, so integers not both 0, and the statement is that there exist, actually let me make a notation, let's let D be the GCD. The statement is there exist integers x and y such that the GCD is ax plus by. Okay, we talked an awful lot about this theorem and we never technically proved it, actually. This is what we use the extended Euclidean algorithm for to find x and y. You could take all the ideas of the extended Euclidean algorithm and basically turn it into a proof if you want. That'd be a sort of a constructive proof that explains exactly where x and y come from. But anyway, we're going to not do that. We're going to just give a different proof of this fact. And our proof of this fact will be, as I said, actually non-constructive. So what that means is we'll prove the theorem is true, but the proof won't really give any indication of how one would find x and y in practice. We already know the answer to how to do that. It's extended Euclidean algorithm. But as far as the proof goes, it won't really explain that part. Okay, but it will justify that this is true. So this is just meant to be an application of the idea of the well-ordering principle. So this can be proved using that as follows. So we're going to let S is going to be the set of all positive linear combinations of A and B. So let me write that out and be a bit clear about it. So we're talking about all the linear combinations of A and B, so anything that looks like this, with the property that AX plus BY, the linear combination, is strictly positive, and also x, y are integers. So just in case there was a small amount of ambiguity, when I say positive linear combinations, positive is not a reference to x and y being positive. No one's saying x and y are positive. What it's a reference to is the result of this expression being positive. Okay? So all the linear combinations you can make which turn out to be positive, these are integers x and y. Okay, so this is a set of integers. It's in fact a set of positive integers by definition, because I said they're positive. In fact, it turns out to be non-empty, so we're going to apply the well-ordering principle in a second. The set is non-empty. This is one of these places where people will say why as an invitation for you to make sure you believe that fact without necessarily spelling it out. But this is the minor thing about this, I'll spell it out mostly, is that no one said A and B were positive. But if, just in the case that A and B are positive, certainly when you start making, you can easily make things like this that come out to be positive. Even if one of them's positive, you could easily make something like this be positive by just using a positive one and a positive coefficient. But even if they're both negative, you could still make this be positive because you're allowed to use negative coefficients. Okay, but there will always be something in this set.
How would we formally state that, though? Could we just say that, hey, we can use it?
How is it that it's non-empty?
Yeah.
I mean, I think you would formally. You're trying to be very careful and formal. You just do it by cases.
Okay.
And say something like, assume one of them is positive, and then you could take that times one. Show something really explicit.
Yeah.
And and then even if they're both negative, you could take them times minus one, and then you say, well, that's positive. Yeah, so it'd be like that's how you do it. You have to handle it by cases. Okay, but we won't fill that in formally right now. But let's apply the well-ordering principle to this set. So it'll tell us that there is a smallest positive thing in this set. And the aim of our proof actually is to prove that that thing is the GCD. So by the well-ordering principle, we get a smallest element. Excuse me, there is a smallest element. Say the set S has a smallest element D. That's what we're going to call it. And what we're going to prove, I guess the notation clashed. Well, I mean, it's going to turn out to be the GCD, but we have to prove that. So we'll prove D equals the GCD of A and B. So anyway, what we do know about D so far, it's not much just yet, but we know that D lives in this set, which means D can be realized in this form. Okay, so what we know is, I guess we know D is positive, and there exist integers. Here I'll call them x naught, y naught, with the property that D is ax naught plus y naught. Sorry, b y naught. Okay, so we've got the smallest element. We want to prove it's a GCD. That entails a couple of things. Right? How you prove something's the GCD of A and B is, well, you have to prove it divides A and B. First of all, if it's supposed to be the greatest common divisor, we have to prove it is a divisor of A and B. And then moreover, we have to prove that it's the greatest of the common divisors. So any other common divisor should be smaller than it. So we have some work ahead of us. So if we're going to prove it's the GCD, we have to show it divides A and B. So let's start by trying to show it divides A. So first, let's show that D divides A. Okay, it certainly is not clear that it divides A based on this one equation we have for D. So we have to do something here. So anyway, this is one of these places where when you want to show something divides something else, sometimes it's good to invoke the division algorithm and talk about remainders and see if you could argue why the remainder has to be 0. So we'll do that here. So let's divide A by D. And so by the division algorithm, what we can do is get a Q and an R. With the property that, so we're going to divide A by D. So A is and the remainder is smaller than d and greater than or equal to 0. So what we want to argue at the moment is that the remainder is 0. Right? If the remainder is actually 0, that says a is d times q, so it's a multiple of d. Right? So d divides a exactly when that remainder is 0. So we'll show r is 0. Because that will do this for us. So anyway, suppose it's not. Okay? Suppose it's not 0. As in like I'll say a proof by contradiction. Okay? So suppose it's not 0. So what that means is it's positive, because it's not 0, and it's non-negative already. But it's also less than d. We know if it's not 0, then it's somewhere strictly in that range, right? Okay, but anyway, here's the thing. So what do we know about r? Is it comes from this equation over here. Okay, so r is a minus dq. Right, that's what we know about r from how it was defined over there from the division algorithm. And then we know something about d, which is that it's a linear combination of a and b. And so when you think about what that will imply this whole thing is a linear combination of a and b, because this will be a linear combination of a and b, and that's an a. So let's see where this takes us. So you have a minus ax naught plus by naught times q. And that's what d is. And then these are all just terms with a's and b's. Okay, so this looks like, where are all the a's? Let me write one more step here. So we have a minus aq x naught plus bq y naught. Okay, so what we have is a times 1 minus qx naught plus,
It's minus BQ.
sorry, thank you. Yeah, this is minus, right? And then it's okay. All right, and then let's say plus b times minus q y. Good. The point, though, is this is a linear combination of a and b. Right? So this is a linear combination of a and b. And also r is positive. So this fact combined with the fact that r is positive implies r is in the set S. Okay, so the r built this way because it was, again, strictly positive under our current assumptions. And it's a linear combination of a and b. Puts it in the set S. But now we have a problem because r was also built to be smaller than d. And so r is less than d. D was supposed to be the smallest element in S, so that's a contradiction. So you cannot be in S and be less than the smallest element of S. That's a contradictory. So this is a contradiction. Okay, so what's it a contradiction to it was back up here when we said suppose the remainder is not 0. Okay, so thus the remainder must be 0, and therefore d is a divisor of a after all. Okay, so that's all that little proof by contradiction. That was just to show this d we built divides a. The good news is that it's a 100% symmetric argument to show that d divides b. We don't have to do it again, right? So a and b have like a completely symmetric roles in this story. So we're entitled to just say similarly. One can show that d divides b. so what we've got from this argument at this point is we have a comment divisor. Okay, so now what remains to show is it's the greatest common divisor. So why is it the greatest? Well, one way to show something's the greatest of anything is to take something else of that group of anything and show that the other thing is less than it. So what we would do here is let E be an arbitrary common divisor of A and B. So suppose we just took an arbitrary integer that divides both A and B. And this is actually the short part. We already know that D is a linear combination of A and B, so actually any integer that divides both A and B divides D, right? So, so the point here is that it follows that E divides this thing, right? Because this is an old fact. Any common divisor of A and B divides any linear combination of A and B. So what are we saying here? Is that E divides D, because that thing is D. So there you go. That's basically it. So if E divides D, E is not going to be E has to be less than or equal to D. Okay, so let me just tack on. This is actually a slightly important fact, but D is positive, so it follows that E is less than or equal to D. So any divisor of a positive integer is less than or equal to that positive integer. Okay, and so that's basically the end of the story. So therefore, D is the GCD. Right, so this last little chunk of proof here says, given any arbitrary common divisor of A and B, it must be less than or equal to D. Right, so therefore, D is the greatest of all the common divisors. It's larger than all the other ones. Okay, so that's the proof. So the proof was, all the proof went into was justifying why D is the GCD, not so much justifying how to make this equation. I sort of started with the equation in a sense and just had to prove this thing was the GCD. Okay, so anyway, consequence of this, well, that's the end of the proof. Pause before I start talking about consequence. Do you have any questions about the proof specifically? Yes?
So are there any general properties that lead to well ordering? So for instance, is countability necessary, but it's obviously not sufficient since the rationals are not well orderable, but they're countable.
Just like in general for like a...
Yeah, like if you take a set with an ordering on it, when is it well orderable?
With the given order. Right? Like
Yeah.
You're not asking about like
Yeah.
producing and ordering to make it well ordered.
No.
No. I'm not sure I have an answer for this question. Maybe we could chat for a minute after, make sure I can fully get exactly the question, and then I'll see if I know anything. I don't have a good answer off the top of my head. Let's see that. Yeah, I think there's different properties about like making your own crazy order into such that it is well orderable, but that's probably not what you're asking about. Anyway, let's, all right, let me just say a couple extra things just in the last few minutes. But are there anything about this specific group before I erase anything? So there is a consequence of this fact. Which I want to point out. Note argument shows something for us, which is worth saying out loud. I mean, how do we produce this, or how do we do this argument? Was we took the smallest positive linear combination of A and B and then proved it was the GCD. So the argument actually shows us something, which is that the GCD of A and B is the smallest positive linear combination of A and B. So there was something I guess I want to say, which is that there's sometimes misconceptions about some things here. So let me just make some remarks. Right? So let's, adopting this notation, okay, D is the GCD of A and B. Something that we just proved, which we've been talking about a lot. Actually, let me take this away. I want to build this into a statement. So here's a remark. So D equals the GCD of A and B implies that there exist integers x and y such that ax plus by is d. Okay, so this is what we've just been proving and what we've used a couple of times. And it's a useful way to sometimes take information about a GCD and work it into an argument. Okay, the thing I really want to point out is that the converse is not true. Okay, the converse of this statement is false. These are not equivalent things. So the converse, which is like what you get if you reverse the arrow. Okay, and this is like one thing that I see people make mistakes with, right? So if you're in a situation where you happen to just know that for some integer d, ax plus by equals d, that does not mean that the d is the GCD. Okay, in fact, you know this already, maybe you don't realize you know it, but just the entire discussion of Diophantine equations involved us talking about solutions of equations like this, where you have some number over here. And it did not have to be the case that the number over here was the GCD. In general, it's a multiple of the GCD. Right? So the way you would amend this if you wanted to try to write the converse is you would have to basically change it. All right, so we're in the last minute. So the way you would kind of fix it is if you knew there exist integers x, y, such that ax plus by is d of, let me say c. What this implies is the GCD of A and B divided c. Like if you wanted to try to make a converse statement, the wrong thing to say is that this is the GCD. The right thing to say is that this thing's a multiple of the GCD. Okay. But anyway,